Hello, everybody, and welcome back to another Teach Astronomy booked stream. I usually say Teach Astronomy anything stream, just Teach Astronomy stream, and I've thrown myself off already because I said book stream. But hello, and welcome to another Monday stream. My name is Victoria, but you can call me Vicky. And ooh, my mic just shook. Apologies. Today we are doing book stream. Like I said, like 3 times. It seems like we don't have too many people here yet, so I think I'll probably give it another minute or two before we start, because I know some people who tune in every week, sometimes they get the notifications late and stuff, so we'll give them a minute or two. Hi, Mahika15, how you doing today? If you guys are here, and sometimes it just doesn't refresh the viewer numbers in my my program, so let me know, sound off, tell me how your day is going so far. For me, it's only 10 in the morning, so my day should have started earlier than it did, but I slept in. So I've got no makeup on today. It's one of those days, you know. Right before the holidays, starting to wind down on work things and getting ready to chill. I mean, holidays are different this year, so it's not like getting ready to go on vacation or anything. So it's more just like getting ready to continue hanging out in the house, but without work to do for a few days. So that's kind of nice. I hope everyone else is doing well. Yeah, like I said, we on this stream, on our Monday streams, we read a book called Einstein's Monsters by Professor Prof Impey. He is kind of the catalyst for this channel, like the figurehead of the channel. The king of the channel, one may say. He's the leader of our group, and he is a professor at the University of Arizona, and has been for a very long time, and has done a lot of cool things in astronomy. And he wrote this book, and it's all about black holes and their history, their discovery, and their science. But for people who might not have, an astrophysics degree, so. It's very cool. We're on chapter 6 today. If you missed some of the earlier chapters, don't worry. They are all on our YouTube channel, which is just YouTube / Teach Astronomy. And you can totally catch up on those there. But you should hang out today, because it's not really it's kind of linear, but it's also a nonfiction book. So it's not like you're missing, plot pieces from some sort of, novel or something. All right. Well, I guess we'll just start on up. It still doesn't seem like there's too many people here, but that's okay. Maybe people are not coming because of the holidays. That is fine. But we can just get started. So, hey, Ace's Hammer, how you doing? Welcome to the chat. So, this chapter is, like I said, number 6, and it's black holes as tests of gravity. Newton's law of gravity is only an approximation of the deeper level of reality described by Einstein's theory of general relativity. When the force of gravity is strong, the bizarre behavior of curved space-time manifests. Light bends, clocks run slow, and intuition fails us. A century after it was first published, Einstein's theory has passed all of its tests with flying colors, but almost all of the tests have been situations of weak gravity. A black hole is the ultimate proving ground for general relativity. In a black hole, the distortions of space and time are extreme. At the event horizon, time is predicted to freeze. At the photon sphere, a distance 50% farther from the singularity than the event horizon, photons are predicted to orbit like satellites orbit the Earth. Gravity this strong cannot be created in any lab on Earth. Ideally, we could run tests on a black hole fairly close to the Earth. However, the nearest stellar mass black holes are hundreds of light years away, and the nearest supermassive black holes are millions of light years away. Therefore, astronomers must use distant black holes to devise experiments to test gravity in new ways. Gravity from Newton to Einstein and beyond. Black holes could only be understood with Einstein's theory of gravity, but they're not the reason a new theory of gravity was needed. That story starts in England in 1665. At the age of 23, Isaac Newton had already failed as a farmer, so his mother had sent him to Cambridge to study. The university was shut down due to plague, and Newton was forced to stay home, where he thought about gravity. That sounds too familiar right now. Twirling a rock on the end of a string, he could see that the rock wanted to fly outward, but the string provided a counteracting force. So what was the counteracting force that kept the moon orbiting the Earth and the planets orbiting the sun? By 1687, he had deduced the answer: a force diminishing with the inverse square of the distance. Newton detailed the theory of gravity in his masterwork, Principia Mathematica. Astronomers were soon using the law to make increasingly accurate predictions. The comet that bears Edmund Halley's name was predicted to return in April 1759, and when it did, Newton's reputation was burnished. A century later, French astronomer Urbain Jean-Joseph Leverrier was pursuing an anomaly in the orbit of Uranus, the first new planet to be discovered since antiquity. He deduced that it was perturbed by something exterior to its orbit, and he predicted the mass and position of the interloper. Neptune was discovered and almost immediately at the Berlin Observatory. It seemed there was no limit to the explanatory power of Newton's theory. Hey Turbo Slayer, how you doing? My weekend went well. The weekend's over for me. It's Monday already. I don't know if you get a long weekend. Hi Charlie, how you guys doing? Welcome to the chat. But yeah, my weekend went well. It was very chill. Did a lot of reading. Not this reading, different reading. All right. We will continue. But there was a small dark cloud hanging in the blue sky, the orbit of Mercury. Mercury has a highly elongated orbit, and its closest approach to the sun, the perihelion, shifts by 50... Sometimes numbers are hard. So it shifts by 5,600 arc seconds per century, as seen from Earth, about 1.5 moon diameters. Leverrier's best Oh, thank you for the cheer, Ace's Hammer. Appreciate that. I like the number choice. Thank you so much. All right. So Leverrier's best calculations show that the known planets and Newton's law could only explain a precession. I'm sorry. I'm only like a third of the way through my tea this morning. I'm just going to start. Okay, have a good one, Ace's Hammer. Thanks for stopping in. Thanks for those bits and everything. Good luck with your day work. I'm going to start back at the beginning of this section, honestly. I feel bad for people watching on YouTube because they're like, what is going on? But I'm flubbing words, so. Okay. But there was a small dark cloud hanging in the blue sky, the orbit of Mercury. Mercury has a highly elongated orbit, and its closest approach to the sun, the perihelion, shifts by 5,600 arc seconds per century as seen from Earth, about 1.5 moon diameters. Leverrier's best calculations show that the known planets and Newton's law could only explain a precession of 5,557 arc seconds. Such was the confidence in Newton's theory that an undiscovered interior planet called Vulcan was hypothesized to explain the tiny difference. Leverrier died believing that Vulcan would be found, but it never was. In fact, Newton's theory was flawed. In 1907, Einstein was just 2 years removed from his miracle year, when he redefined physics, but he wasn't trying to improve on Newton's law of gravity. He was working in the patent office in Bern, with plenty of time on his hands. Then he was startled by his happiest thought, that a person in free fall would not feel their weight. This notion impelled him towards a radical new way of thinking about gravity. 8 years later, Einstein was in turmoil. He'd done most of his early work alone. Academia belatedly embraced him, and he had become a professor of physics in Prague, but it was an uneasy situation. Anti-Semitism was on the rise in Europe, and Einstein experienced it directly. It may be hard to believe, but Einstein struggled with the math of general relativity. He was at his most comfortable relying on his extraordinary physical intuition. For years, he sketched out versions of the theory, but there were always flaws and omissions. In the summer of 1915, he gave a series of lectures on relativity at the University of Göttingen. And in November 1915, he made a breakthrough, which he presented in his fourth lecture. Whoa. When he presented in his... It's Monday, guys. Jesus, okay. In November 1915, he made a breakthrough, which he presented in his fourth lecture at the Prussian Academy of Sciences, titled, quote, "The Field Equations of Gravitation." His crucial test of the equations was whether they could account for the anomalous shift in Mercury's orbit. The theory predicted an effect of 43 arcseconds per century, exactly the difference between what was observed and what Newton's theories predicted. Quote, "I was beside myself with joy and excitement for days," Einstein told a colleague. "The results of Mercury's perihelion movement fill me with great satisfaction. How helpful to us is astronomy's pedantic accuracy, which I use to secretly ridicule." In Newton's theory, the source of gravity is mass. In Einstein's theory, mass is part of a more general quantity called the energy-momentum tensor. Think of a tensor as a fancy version of a vector, with information about a physical quantity at every position in space. Mass in general relativity is defined in curved spacetime and has energy and momentum in each of three directions. So in Einstein's theory, it takes 10 equations to describe the relationship between mass and spacetime. That's as far as we can go without joining the Mad Hatter and jumping down the rabbit hole of coupled, second-order, partial differential equations. General relativity was just one of the foundational physical theories of the early 20th century. The other was quantum mechanics, which explains the behavior of atoms and subatomic particles. These theories of the large and the small are incompatible. Relativity is smooth because events in space are continuous and deterministic. Everything that happens has an identifiable local cause. Quantum mechanics is grainy because changes occur discretely by quantum leaps, and outcomes are probabilistic rather than definite. The most bizarre example of dissonance between the theories is quantum entanglement, in which properties of particles can be coupled instantaneously over large distances. Einstein derided this as spooky action at a distance, and was convinced there was a deeper theory of nature that would remove the weirdness of quantum mechanics. He failed in his quest. Despite many attempts, Einstein couldn't find fatal flaws, or even poke significant holes in quantum theory. He tried to generalize his geometric theory of gravity to include electromagnetism, leading him to become frustrated and increasingly isolated in this research. When he died in Princeton in 1955, he left an unsolved set of equations on his blackboard. The mantle, or perhaps the burden, of reconciling these two great theories has been taken up by succeeding generations of physicists. The ultimate goal is a theory of everything that will explain all physical phenomena. There are 4 fundamental forces in nature. 2 apply on a subatomic scale, the strong and weak nuclear forces, and 2 apply over very large distances, electromagnetism and gravity. Physicists went some way toward unifying these forces in the second half of the 20th century. Accelerator experiments in the 1970s showed that electromagnetism and the weak force that's responsible for radioactivity are manifestations of one electroweak force. Additional experiments have almost succeeded in bringing the strong nuclear force into the mix. This edifice is called the Standard Model of particle physics. But gravity stubbornly resists being part of this model. Nobody has ever seen a graviton, the hypothetical particle that carries the gravity force. Unification that brings in gravity may only occur when the temperature is a fantastic 10 to the 32 Kelvin. And the only situation we know of with that temperature is 10 to the negative 43 seconds after the Big Bang, when the universe was the size of a fundamental particle and general relativity crashes and burns in the initial singularity. And we have a figure. Let me pull that up. Here's our figure. So this says, the four fundamental forces of nature consist of two with infinite range, gravity and electromagnetism, and two that operate on subatomic particle scales, or subatomic scales, the strong and weak nuclear forces. They all have very different strengths, but there is evidence that at extremely high energies, they unite into a superforce. So the unification of weak and electromagnetic forces was seen at accelerators in the 1970s, and there are hints of a grand unification with the strong force. So you can see how we've got so many things here. We got gravity down here. We got magnetism and electricity, which makes, electromagnetism. We've got gravity. We got the strong nuclear force, and we've got the weak force. And so this is just a way to kind of throw them all together. It's an interesting kind of drawing. It's a little confusing. I mean, not confusing, but a little clunky. I don't know. But it's from CERN, so must be good. Oh, yeah, it's the conjunction today. Let me know if you guys are going to be going to see the conjunction. Oh, you got a picture there too. That's cool. I can show you guys really quick. Is that Parzival? I think that's Parzival. I think he got a new username. But this is what he just sent me, so you can see the there it is. There's Saturn and Jupiter. Very exciting. Happening either now or tonight, depending on where you live. Oh, by Jasker. Is that a person that's part of the... Is that a person that's in our Discord group? I believe so. It's very exciting. Yeah, I went outside to look yesterday, and obviously they're not as close as they're gonna be. But it still looks super cool. It's very exciting. All right, I'm gonna finish this section, then we can talk more. All right. There are several approaches to quantum gravity. Quantum loop gravity follows the thought process of Pythagoras, who imagined cutting a stone in half and half and half again until a limit was reached. Oh gosh. Books flopping all over the place. Okay. In this case, an inch is divided in half and half and half again until atoms, or indivisible units of space, are reached. Quantum loop gravity is an attempt to directly extend the formalism of quantum mechanics to the gravity force. The more radical approaches involve string theory and extra dimensions of space beyond the familiar three. Going from Newton to Einstein to beyond, from rigid and linear to supple and curved to evanescent and grainy, is the most important unfinished project in physics. Progress has been slow, and the work is fiendishly difficult. We saw in Chapter 1 that black holes are not only situations of extreme gravity, but also situations where quantum effects are important. Any new theory that reconciles the smooth world of curved spacetime with the grainy world of subatomic particles will meet its most important challenge in black holes. Einstein once said there are only two things that might be infinite: the universe and human stupidity. And he wasn't sure about the universe. Some of the smartest humans on the planet are trying to come up with a theory of quantum gravity. They might succeed, but they might not. Meanwhile, progress can be made by testing and trying to break general relativity. As another great physicist, Richard Feynman, said, quote, "We are trying to prove ourselves wrong as quickly as possible, because only in that way can we find progress." And that's the end of that section. You said you're fascinated by the conjunction. Yeah, it's really exciting. I wish we had a bigger telescope here or something, because me and my partner both have like bigger telescopes at our parents' houses. Granted, our parents' houses are different places in the country. So Matthew Matthew will definitely be going out tonight. I don't think he'll be able, because we talked about it, and I don't think he's going to be able to stream it because he's just got too much stuff going on with his little kids and everything. But he'll definitely, I think, try to take some pictures with that smartphone mount that he has now. So hopefully we'll be able to see those. And I think, yeah, we're not doing amateur astronomy this week because it's Christmas on Friday. But the stream tomorrow is going to be Professor Impey's Q&A stream. So I'm sure he'll talk about the conjunction. And then Wednesday, me and Michael are just going to compile a bunch of pictures for all of us to look through. So hopefully we'll have some from Matthew. If not, then we'll just find some really cool ones from online and find some really good astrophotographers, because it's going to be really cool. We've got some binoculars. So yeah, definitely, if you guys haven't heard about this, which you probably all have, but just to be sure, tonight, or today or whenever, depending on where you are, but the 21st is the conjunction of Jupiter and Saturn. So they're going to be the closest they've been in, I believe, I'm not going to look it up now, but I believe it's like 200 years. It's been at least 200 years since they've been this close in the sky. And granted, I don't think they're 800 years, a lot more. Thank you. So it's been like over 800 years, and it's going to be another huge amount of time until it happens again. 1623. Okay. So 500-ish, about 500 years. Yeah. And then the next time, yeah. So like he's saying in the chat, it's a very long time that, until this will happen again, and we'll probably not be here anymore. But, it's just a cool thing to see, especially if you have some powerful binoculars or like a little telescope or something, and then you might be able to see the rings too. But they're like right next to each other in the sky. Be sure to get out there. I'm pretty sure the best time, at least for me, the best time to see it is like right after sunset, because they're setting relatively quickly in the sky, at least in the northern hemisphere. It might be different in the southern hemisphere. But yeah, go out, check them out. It's going to be really cool. And we'll talk about it more on Wednesday. I mean, I don't want to think about it, but it's true, right? This is the only one we're going to get to see. So you got to go do it. I mean, there's probably going to be another, I don't know when another conjunction of like any planets is going to be that we can see, but this one is like, at least for Saturn and Jupiter, this is the big one. So, all right. So we will continue. So what black holes do to space-time? A black hole can be defined as a region of space-time so curved that it is pinched off from the rest of the universe. But even at some distance from the black hole, space-time curvature will cause particles and light to be deflected. When Einstein developed general relativity, no black holes were known. So his theory was tested with a much more subtle effect: the slight deflection of light from a distant star as it grazes the sun on its way to the Earth. This is most easily observed during a solar eclipse, when the sun is blotted out by the moon and the background star is visible. In 1919, just 3 years after the theory of general relativity was published, Arthur Eddington and his colleagues measured the deflection simultaneously from Brazil and South Africa. It matched Einstein's prediction. The result made the front page of most newspapers. The drama was undoubtedly heightened by the symbolism of a British scientist confirming the work of a German scientist at the end of a long and bloody war. Einstein became a celebrity overnight. He was supremely confident about the outcome. Asked what his reaction would have been had general relativity not been confirmed by the expedition, he said, "Then I would feel sorry for the dear Lord. The theory is correct anyway." What's going on in the chat? Yeah, Saturn and Jupiter conjunctions do occur more often than this, but I'm pretty sure this is the closest that they're gonna get in a really long time. Yeah, so they always pass pretty close to each other. But this is a really special one because of how close they're going to be. Yeah. All right. So, mass bends light. Given the importance of this fact for Einstein's theory and reputation, it's surprising that he was slow to recognize the broader implications. He knew that if light rays passed close to a sufficiently massive object, they could be bent enough to converge and produce a magnified image, or multiple images, of a background source. As the process resembles the bending of light through a lens, researchers call it gravitational lensing. At the urging of an engineer colleague, Einstein finally published a paper on lensing in 1936, with this strikingly diffident preface. Quote, "Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish." End quote. He wrote a self-deprecating note to the editor of the journal. Quote, "Let me also thank you for your cooperation with the little publication, with which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." End quote. Einstein was dead wrong about the value of gravitational lensing. It has become an essential tool in modern astrophysics. It has been used to map out the dark matter in galaxies and across the universe, to measure the geometry and expansion rate of the universe, to constrain dark energy, to do surveys for brown dwarfs and white dwarfs, and to detect exoplanets smaller than the Earth. Oh, and we have a figure. Great. Oh, nope, not that one. There we go. So here's our figure of gravitational lensing. So essentially it's just showing that from where we are on Earth here, if there's a galaxy cluster here and a galaxy back here, the galaxy behind light will be bent and space-time will be distorted because of this galaxy in front of it. So we'll be able to notice that distortion. So it's saying this and this are the lensed galaxy images right here. Yeah. And it says, since the lensing is caused by all mass, not just visible matter, this is a way to measure the amount of dark matter in the universe. Very cool. All right. Einstein thought the lensing effect would be too small to be measurable. But within months of his paper, Caltech astronomer Fritz Zwicky realized that billions of stars combined within galaxies could produce observable lensing. In a prescient paper, he outlined essentially all the modern uses of gravitational lensing. However, it took until 1979, more than 40 years, for lensing to be observed. The tool was a supermassive black hole billions of light years away. A group of researchers led by British radio astronomer Dennis Walsh found two quasars. Found two quasars with identical spectra using the 2.1 meter telescope at Kitt Peak. The odds of finding two quasars with identical spectra so close in the sky were very low. So low that on his way to Kitt Peak, Walsh wrote a bet on the blackboard of his colleague Derek Wills. No QSOs. I pay Derek 25 cents. One QSO, he pays me 25 cents. Two QSOs, he pays me $1. Walsh recalled. When I called Derek the next morning and told him what we had found, we laughed, and I said, "You owe me $1. Suppose I had said to you, 2 QSOs, same redshift, $100. Would you have taken it?" He said, "Of course." So I lost $99 and kept a friend. I had 4 teenage sons, none particularly interested in science. So when they asked me, what good is gravitational lens? I was able to say, well, I made money out of it. The quasars looked like identical twins. But rather than two quasars that just happened to have the same spectra, they were more like a mirage. Light from one quasar took two different paths around an intervening galaxy, giving two images. A massive galaxy bends light very subtly, by only 1,000th of a degree. In this first gravitational lens, light travels for 8.7 billion years to reach us, but it travels just over a light year farther, going past one side of the galaxy compared to the other. Since the light from the quasar varies in brightness, there is a time delay of just over a year in the variations seen in one image compared to the other. This has been used for a clever measurement of the expansion rate of the universe. Oh, big chats. What are you guys talking about this evening on the first day? Oh, I see. Yeah, you're just grabbing some of the stuff that people are saying about it. Yeah. It's a very exciting conjunction. Yeah, it's something like it's been a really, really long time since they've been this close. Something like 1623 or 16... Yeah, 1623, and then... But technically they happen every 20 years, but this is going to be a really exciting one. So even if it does happen every 20 years, it's still 20 years, you know? It's exciting. You're not going to see the next one for another till 2040, which sounds like a fake year, but 2020, to be fair, it sounds like a fake year, both in name and in what's happened. Oh, Pixel said in 1226 it was pretty close too. They checked it out in Stellarium. Yeah, Stellarium's cool. If you guys are ever interested in like playing around with a virtual planetarium for free, Stellarium is very cool. 20 years, so many children's per minute. All right. Let's see. Where were we? I think we were here. Oh, Star Walk 2 and Space Engine I've heard are also both really good. And someone else mentioned something else. Open Space or something. There's a few that are really excellent, so yeah. All right. Gravitational lensing is rare because it depends on a near perfect alignment of a background quasar and a foreground galaxy. With many thousands of quasars studied, less than 100 cases of lensing have been found. In a dozen of them, the alignment is perfect. So instead of multiple images, the intervening galaxy turns the quasar point source into an Einstein ring, an exquisite display of general relativity in action. Depending on the geometry, light from accretion energy near a supermassive black hole appears as an arc, multiple images, or a perfect ring. When the Hubble Space Telescope started work in the 1990s, another type of lensing situation was discovered. Instead of light from a single quasar being lensed into multiple images, light from numerous distant galaxies is lensed by an intervening galaxy cluster. Sometimes multiple images are formed, but more often the background galaxy light is sheared into an arc. The signature of this type of lensing is a cluster surrounded by little arcs arranged in concentric circles around the center of the cluster. And we have another figure. So many figures. Here we are. So I think this is an image. Yeah, this is an image from Hubble in the 80s. So it says in this image, Able 2218 is causing the distortion and magnification of many more distant galaxies. The lensed arcs form concentric circles around the center of mass of the cluster, and in some lensing situations, one distant galaxy can have 5 or 7 separate images. So you can see how everything's distorted there because of the galaxy in the foreground. So, each distorted image is an experiment in gravitational optics. Several hundred clusters have shown these arcs, so astronomers have accumulated tens of thousands of examples of mass-bending light. All mass bends light, whether it's visible or not. So lensing is the best tool astronomers have for mapping dark matter in galaxies, in clusters, and in space between galaxies. Lensing provides the best evidence that dark matter exists and is a dominant and pervasive component of the universe. That's the end of that section. A molten ring type-ish? What is a molten ring? I mean, just like a ring in a volcano? Is that a molten ring? We're looking it up. I found a molten ring of actual... Oh! Yes, like a molten ring. Apparently, I don't know if this is what you were referencing, but apparently a little while ago, NASA posted something about... they shared this image. I'll show you guys. And said, if you like it, then you should have put a molten ring on it. Which is so cringy, but pretty funny. It's a cool image, though. You can see the distortion, and it does look like a molten metal or something. Yeah, it's pretty cool. Salvaseria said there's a video by Veritasium. Yeah, Veritasium has really great stuff if you guys are looking for somebody to watch. I mean, we have great stuff too. But Veritasium does some really cool things. A lot of him and like Mark Roberg and stuff. That's Mark Rober. I always add like a G at the end of his name. And Vsauce, yeah. A lot of those were kind of our inspiration for our other channel, Active Galactic on YouTube, where we do like short, like highly edited science videos about different topics and stuff. Also, sorry if you can hear that. Someone has decided to leaf blow outside my window, even though it's just concrete outside my window, so I don't know what they're doing. Gotta love living in an apartment, you know? All right, so Mark Rober, the Curiosity rover engineer. Did he work on it? Drying the concrete, yeah. Gotta make sure it's nice and dry. I did not know that. I knew he had worked for NASA doing something at some point. I didn't know he worked on the Curiosity rover. That's really cool. Yeah, he does some really cool stuff. I love his, he has a series, I think it's only a couple videos, but he does the, what's it called? To counteract porch pirates, they call it. So when people steal people's packages, especially like during the holidays and stuff, a lot of people will go, because like people are terrible. They'll go and they'll take boxes that are sitting, like that people have gotten, like packages and stuff, and they'll steal them off of people's porches if they're not home. And to counteract that, he made this like the perfect like anti-porch pirate box. So he put like a glitter bomb in it, and like some sort of like terrible like sulfur some sort of like terrible like fart smell release thing, and then like an alarm that says like the police are being called and stuff, and this whole thing, and it's very funny. It's a good series if you guys want something to watch that's really funny, but also really impressive from a engineering standpoint, because he builds all this stuff himself. It's pretty cool. He also made an obstacle course for squirrels. That was fun. All right, let's continue. How black holes affect radiation. The event horizon of a black hole is a place where time stands still and radiation stands still. It's a premise of Einstein's special relativity that light has a universal and constant speed of 300,000 kilometers per second. Light leaving a black hole struggles against gravity so intense that its speed is quelled, its energy sapped. The effect is called gravitational redshift. The event horizon of a black hole corresponds to a place where the redshift is infinite and light is trapped. Without a black hole to test the theory on, how can we understand what gravity does to radiation? Let's use a thought experiment situated on Earth. Imagine a tower where we send a photon from bottom to top, turn its energy into mass, according to E equals mc squared, let the mass drop to the bottom of the tower, and turn it back into a photon. Sounds straightforward. But wait. If we drop the mass, it picks up speed and gains gravitational energy. The amount gained is mgh, where m is the mass, g is the acceleration due to Earth's gravity, and h is the height of the tower. When we turn the mass back into a photon, it has more energy. We could keep doing this over and over and create energy and get rich. Since nobody has made money by cycling light up and down, there must be a flaw in our assumptions. The only way to conserve energy, in other words, keep the energy the same, is in this scenario, is to posit that light is affected by gravity in the sense that it loses energy as it climbs away from the Earth's surface. Losing energy means that the light shifts to a longer or redder wavelength. This is gravitational redshift. Imagine a clock based on the frequency of light. Put the clock at the bottom of the tower. If we observe from the top, the photons lose energy reaching us, so they decrease in frequency. We see the clock running slower. Conversely, if we're at the bottom of the tower looking up, a clock at the top will run slightly faster. Time passing more slowly in strong gravity is another prediction of general relativity. An amusing example, attributed to the physicist Richard Feynman, is the prediction that the center of the Earth is 2.5 years younger than the surface. It's called gravitational time dilation. The redshift and time dilation effects are closely related. Light and other forms of electromagnetic radiation have a wavelength that's inversely proportional to frequency. As light's energy is diminished in its struggle against gravity, its wavelength gets longer or redder and its frequency gets smaller, which is the same as saying that light's clock is running more slowly. The first observation of gravitational redshift was made by Walter Adams in 1925. He measured the shift in the spectral lines of the nearby white dwarf Sirius B. As it is part of a binary system, its mass is known, and the shift is a few parts in 10,000 in wavelength, compared to a few parts in a million for a less compact star like the Sun. Unfortunately, the measurement was flawed by light contamination from the far brighter companion Sirius A, so scientists didn't consider the effect confirmed. The first laboratory test of general relativity was an experiment by Robert Pound and his graduate student Glenn Rebka in 1959. They measured the spectral shift in gamma rays from radioactive iron traveling 22.5 meters up a tower on the Harvard campus. The tiny loss in energy, less than 3 parts in 10 to the 15, confirmed the prediction of general relativity at the 10% level. And we have a figure. There it is. So this is a figure explaining the first experimental test of general relativity in 1959, which is what we were talking about with Robert Pound and Glenn Rebka. So they measured the energy of gamma rays from an iron-57 radioactive decay traveling upward and downward over a distance of 22.6 meters. The photon traveling downward was blue-shifted, and the photon traveling upward was red-shifted by exactly the amount predicted by general relativity. The experimental precision required for this test was a few parts in 10 to the 15. So you can see this is the iron source, iron-57 source. This is the detector, and this is the source, and this is the detector. So it was measuring if you launch the gamma photons up or if you launch them down, if there's going to be a difference, and they notice that there's that difference of the photon traveling downward is blue shifted and the photon traveling upward is red shifted. Are we back? I think we should be. Let me check my Yeah, it seems like I'm getting a feed on my moderator page. Oh, my bitrate is horrific. What is happening? Let me know if you guys can see or hear me or not. Put something in the chat too. Oh, you can. Okay. I don't know what is going on. I don't know if there's something wrong with my internet, but it doesn't seem like there's something wrong with my internet. So if you guys weren't here last week, this happened the same thing happened last Monday, and like an hour later, because we were right at the end of the stream, and I don't know what's up. It's very weird. It's very confusing. It also says I have 0 viewers right now, but it seems like Bossa Nova's here. Charlie's here. And I'm not sure if anybody else stuck around, but hopefully you did. Hopefully other people can see me. If you guys just want to let me know, I'll put something in the chat too. I should be back up. If you guys can't see me, let me know. Or try to refresh the page. Yeah, so I'm using a new program called Streamlabs, and I knew that it was a little buggy, but like most streamers on Twitch use this program, and I've never heard of this happening. I've heard like sometimes your alerts don't come up or something, but this is a problem. So apologies again. Also, since it's being weird now, there also is a chance that things that you put in the chat sometimes are not coming through, because I've heard that is a very common problem, is that people try to chat and they're like, oh, why isn't this person answering me? Like, why isn't the streamer answering me? Like, why isn't anyone talking to me in the chat? And it's because like they just don't show up sometimes, which is very weird. But if that happens, if for some reason you think that I'm like, if it's been a few minutes and you notice that I'm like not answering you, because I can see like Charlie, I can see Salvasuria. Those are the only 2 people I saw that responded yes, that they can see that I'm back. But if you're trying to respond and it's not working, let me know in the Discord, because that could also be a huge problem. I have the Discord up in the background. Oh, you can see now. Okay, cool. Yeah, I don't know what's going on. I'm gonna have to try to figure that out over break, because I don't like that. It's important to be able to, stream for more than 45 minutes without a huge interruption like that. I have no idea why it crashed. It's very weird. Twitch is trying to overtake us. Yeah. Twitch is trying to shut down astronomy education. Part of me is like, do they think I'm reading copywritten material that I don't have access to? I highly doubt that that's the thing, right? Because they would probably tell me if that was the thing. But part of me is like, maybe they don't know that I know Chris and that he said this was okay. I don't think that's it, but I'll try to figure out before we do this again. You can't say that. I'm not going to let you say that. That's inappropriate. But I agree. Twitch. Well, I don't think it's Twitch. I think it's Streamlabs. I think Streamlabs is the problem. And I will try to figure it out before I stream again. But I'm going to go back to reading, because I think you guys, I think it crashed right after I explained the whole that whole diagram. So we'll go after that. Improvements came with the use of atomic clocks as probes of gravity. In 1971, a cesium atomic clock flown at high altitude on a commercial jet gained 273 nanoseconds compared to an identical clock at the U.S. Naval Observatory. And in 1980, a better test used a maser clock flown on a rocket to improve the agreement with relativity to 0.007%. The current state of the art measures quantum interference of atoms. General relativity has been confirmed with the phenomenal accuracy of less than 1/1,000,000%. We can show that a clock actually runs faster when we raise it less than a meter. Astronomers have got in on the act as well. Clusters of galaxies are the most massive objects in the universe. Photons from the center of the cluster, where there are many galaxies, should lose more energy than photons from the edge, where there are fewer. A group at the Niels Bohr Institute, led by Radek Wojtak, looked for this effect, which is so small that they had to combine data from 8,000 clusters to detect it. Once again, Einstein's theory was confirmed. A good thought experiment elicits the reaction, "Of course, that's obvious." Recall the English biologist Thomas Huxley's reaction when he heard about Darwin's theory of natural selection. How extremely stupid not to have thought of that. In Einstein's elevators, the beauty of general relativity is revealed. An elevator free-falling towards the ground is the same as an elevator drifting in deep space, because the gravity force has been removed. And an elevator being accelerated through space at 9.8 meters per second is the same as an elevator on the ground, because acceleration by gravity can't be distinguished from acceleration by any other force. In the second case, imagine you shine a flashlight across the elevator. During the instant of time it takes for light to reach the other side, the elevator is accelerating, so the light travels... Sorry. I'm going to start that sentence over because my inflection did not make sense. During the instant of time that it takes for the light to reach the other side, the elevator is accelerating. So the light travels a downward curve... Nope, did it again. During the instant of time that it takes for the light to reach the other side, the elevator is accelerating. So the light travels a downward curving path across the elevator. That makes more sense. Einstein's theory says the same thing must happen with the stationary elevator on the ground. Light falls due to gravity. Or, in the language of relativity, the mass of the Earth curves space and light bends slightly as it follows the curved space-time near the Earth. So far, we have described the classical tests of general relativity. They use situations where gravity is so weak that space-time curvature and distortion is slight and extremely accurate measurements are needed. Nearly 50 years ago, Irwin Shapiro, the longtime director of the Harvard-Smithsonian Center for Astrophysics, proposed an ingenious weak gravity test of the theory. He realized there would be a slight delay in the round-trip travel time of radar signals bouncing off other planets if the path of the photon took it near the sun. Using measurements of radar bounced off Mercury and Venus, before and after they were eclipsed by the sun, he confirmed general relativity at a 5% level. This test was repeated in the outer solar system by NASA's Cassini spacecraft to give agreement at the 0.002% level. These tests affirm general relativity and its superiority over Newton's theory. But there's something vaguely unsatisfying about testing relativity in places where space is as flat as an Iowa cornfield. It's like test driving a Lamborghini in a parking lot. Sure, it performs better than your old Ford Taurus, but that's setting the bar low. It's much better to drive both cars fast in the mountains, where the Lamborghini powers up the hills and hugs the curves, while the Taurus overheats and careens off the road. Astronomers look forward to eventually testing the theory with black holes, where the effects on radiation should be spectacular. As we'll see in the next section, large gravitational redshifts have been detected from black holes using spectroscopy of the accretion disk. That's the end of that section. Hello, Gooseman Chiru. How you doing? Yeah, if you're just tuning in, it's because you probably got another notification that we were going live, because I had to go live a second time because my stream software crashed again. So that's fun. I'm gonna have to talk to my friend. We have another person at another person that's part of Chris's group that does computer programming and stuff, and he also is a streamer. He's played Among Us a couple times with us, and I'm sipping on my Scottish elixir. Oh yes. I got some chai tea in here today from my old tea company. It's not mine. I worked at a tea shop and they went out of business. It wasn't a small tea shop. It was a bad chain tea shop, but I got to steal a bunch of their tea at the end because they were like, we're gonna throw it away, and I was like, nope, and I took it. They can't do anything about it. But yeah, we had a problem with the program that I used to stream, and it crashed, and I'm going to figure it out before we do this again, because this is happening way too often for my comfort. But I'm really glad that you guys are all still here. Yeah, at least I'll have some time before we do one of these again, because I think I'm going to be taking next week off, probably, since it's the middle of the holidays. I hope that's okay with everyone. I know we're taking off with like everything else we do, because the university's closed down, and Matthew and Chris are like on their own family vacation stuff. I mean, like, they're not going anywhere, but they're spending time with their family. And I would like to do the same. Granted, my family is just one other person that I see all the time, but gonna be Skyping a lot of people. Is anybody doing anything for the holidays? Let me know. This is not the only meeting of the week. Actually, we have Professor Impey wanted to get another Q&A in before the holidays, so we're having one of those tomorrow on Twitch here. I have it on the schedule, I believe. Let me make sure, but I'm pretty sure I have it on the schedule. I do. So it's tomorrow at the same time that we started here. So oops, there we go. Yes, we'll have one tomorrow, and then we have another. He told me that we're having one tomorrow. So I think we're still on for tomorrow. I'll have to ask him, but I'm pretty sure Matthew told me at least to schedule one for tomorrow. But we will be definitely doing our Wednesday stream. Me and Michael will be doing our Wednesday stream, and we'll be talking a lot about the conjunction sharing photos that we find online and stuff like that. What's your profanity? Turbo's there. Say it again, but without the profanity. But yeah, we're definitely Wednesday's happening. Pretty positive tomorrow's happening as well. But yeah. Anyway, yeah, tell me what you guys are doing for the holidays. Tell me if you're, I mean, I guess a lot of you are international, so there might be safe ways to travel for you guys. Hopefully, if you're in the U.S., you're going to be a little careful if you're going to travel. Hopefully, you're not traveling, because, it's bad. And if we can get through a few more months, maybe we'll have vaccines. It'll be okay. There's that. Yes. It's a very nice little message there. We do need more love in this world. But yeah, let me know what you guys are doing. I would love to hear what everyone's holiday plans are, or if you celebrate at all, if you celebrate something different. And I will keep going for now. So, inside the Iron Curtain. The vicinity of a black hole is the ultimate test for general relativity. How close can we get with observations? The event horizon, through which no information can reach us, defines the limit. General relativity also describes several important scales beyond the event horizon. The first is called the photon sphere, where light is trapped and travels on circular orbits around the black hole. Since mass bends light, we can think of mass bending light into a circle. If you could go there, a photon might begin at the back of your head, orbit the black hole, and enter your eye, allowing you to see the back of your head. For a stationary black hole, the photon sphere has a radius 1.5 times the Schwarzschild radius. A rotating black hole has two photon spheres and drags space with it as it spins. The inner photon sphere moves in the direction of rotation, and the outer photon sphere moves against the rotation. Think of a swimmer trying to escape the maelstrom. They hold their ground by swimming against the current. If they swim with the current, they are pulled closer to their doom. Since the photons are trapped, a photon sphere has never been observed. We enter the realm of observation at the inner edge of the accretion disk. As particles are tugged towards the black hole by gravity, they rub against one another, so the accretion disk is a plasma whose temperature decreases going out. The inside edge is defined by an innermost stable orbit that is 3 times the Schwarzschild radius for a non-rotating black hole, and a little bit beyond the event horizon for a rapidly spinning black hole. Inside this stable orbit, a particle plunges into the black hole and disappears forever. The inner edge of the accretion disk for a low-mass black hole has a temperature of 10 million Kelvin, and for a supermassive black hole, it has a temperature of 100,000 Kelvin. Gas this hot emits copious amounts of X-rays. Can we see the inner edge of the accretion disk? No. The angular scale is far too small for any telescope to resolve. A nearby black hole at a distance of 100 light-years has an inner edge that subtends an angle of 10 to the negative 9 arcseconds. That's like trying to see the head of a pin on the surface of Mars. The situation improves slightly for a supermassive black hole like the inactive ones that have been found in the centers of nearby galaxies. They are several million times farther away, but have event horizons a billion times bigger. So their inner accretion disks subtend an angle of 10 to the negative 7 up to 10 to the negative 6 arcseconds. That's a few hundred times smaller than the resolution of the radio interferometers described earlier, so still beyond the reach of observational astronomy. The only way astronomers can peer inside the Iron Curtain is to use spectroscopy. The gas in an accretion disk is overwhelmingly made of ions of hydrogen and helium, but 2 of every million particles are ions of iron. The region just beyond the accretion disk is an extremely hot corona. X-rays from the corona irradiate the slightly colder accretion disk, and their energies are just right to excite spectral transitions of iron. Even though iron is a rare element, these spectral features are sharp and strong. An X-ray spectrum shows how the gas is moving, because the approaching part of the accretion disk is blue-shifted, while the receding part is red-shifted. X-rays from the inner part of the accretion disk also suffer a strong gravitational redshift, so the spectral line of iron is broadened and also skewed to lower energies. X-rays offer the exciting possibility of measuring gravity within spitting distance of the event horizon. And I have a figure for you guys. Grab that. This is what crashed it before. Let's hope it doesn't do it again. Okay. It looks okay for now. So this is, it says the spectral line of iron can be used as a probe of the high temperature inner region of the accretion disk surrounding a black hole. The line is skewed to low energy by gravitational redshift from the black hole. The inner edge is far from the black hole when the black hole rotates in the opposite direction to the accretion disk, retrograde, and closer when it rotates in the same direction, prograde. These differences are seen in the X-ray spectrum. This is essentially just the X-ray spectrum here, and then what it looks like based on these types of rotation. So in all of these, the gases around it are rotating in a certain way, but the X-ray spectras are based on if the actual black hole is rotating and which way it's going. Cool. Yay, it didn't crash. I'm just catching up on you guys. Actually, I'm gonna finish this this section really quick, and then I'll go through chat. These observations were made possible by the launch of the X-ray satellite ASCA, in 1993. The first detection of X-rays from the inner edge of a massive black hole accretion disk followed a year later. Gravitational redshift of X-ray spectral lines has now been seen from a dozen stellar mass black holes and a similar number of supermassive black holes. Then, a puzzling X-ray phenomenon discovered years earlier became a second window onto the vicinity of a black hole. That's the end of that section. Oh, Student McLeod, you're a phase 2 vaccine person. That's very exciting. Oh, and you have a photon sphere diagram for us. Let's see. Trying to click on the right things here. Oh, my Chrome. Hold on. Give me Chrome, please. There we go. Okay. There she is. Gotta open that. Okay. I have too many tabs open and I keep clicking on the wrong ones. Student McLeod just sent this over. So it is a photon sphere diagram. Very cool. So it says, will it hit singularity? Will it escape? Or will it hit singularity? But what path? Or will hit singularity? It will escape. Or will it hit it but have a different path? Very cool. Turbo Slayer Parzival said, your mind is gonna burst. What are these points? Were you talking about something in the book? Because it is complicated, to say the least, I would say. It's hard, honestly. I'll be honest with you guys. It's very tough to fully absorb the material when you're worried about reading it aloud. The black hole thing, yeah. It's a lot. But yeah, the molten ring thing is very funny. I saw that before. Student McLeod said being over 65 years old is not exciting though. Oh, I mean, I'm sure you've had a lot of exciting times in those 65 plus years, right? So that's a fun way to look at it. What did you Dropbox to me? Oh, a secret. If you guys want a link to the book, if you want to reread any sections, if you are also confused about some of the high level stuff, just check out that Dropbox link. But don't tell anybody, because I don't think I'm allowed to really share that. I'm sure 44 years in high school science was exciting. That's still crazy. That's amazing that you did that. I can't teach to save my life. This is the most teaching I've ever done. And it's just reading a book to you guys and trying to figure out things that you all already know. But it's very different. Public teaching. I've done a little bit of public teaching, I would say. You know, that like outreach sort of thing. Through digital media. The new world of digital media. But that's really it. All right, so we will... Where were we? Maybe at the end of the section, right? Okay. Yes. So we'll keep on going. X-rays flickering near the abyss. In the 1980s, when X-ray satellites began monitoring compact stars and star remnants, sources whose X-rays varied rapidly were seen. The flickering wasn't rhythmic, so the phenomenon was called quasi-periodic oscillation. Oscillations were first seen in white dwarfs, and later in neutron stars and black holes. It took a while for astronomers to untangle the astrophysics behind these variations. In different sources, the timescales ranged from a second to as little as a millisecond, and the periodic behavior was often lost in the noise of more chaotic variations. Black holes showed a particular pattern of brightening and dimming, at first taking 10 seconds to complete an oscillation, then weeks or months later speeding up to a tenth of a second before the variation stopped, after which the cycle repeated. Observations and models of the archetypal black hole Cygnus X1, I'm assuming it's X1. Okay, it's X1. It was on the other page. Revealed the source of the variations. They are pulses left by gas as it leaves the inner part of the accretion disk and plunges toward the event horizon. It's thrilling to see the death throes of material falling into a black hole in real time. Astronomers suspected that the frequency of variations might depend on the mass of the black hole. Gas spirals inward in the accretion disk, moving faster and faster, and it piles up near the black hole, releasing a torrent of X-rays. This congestion zone is close in for small black holes, so the X-ray clock ticks quickly. It's farther out for larger black holes, so the X-ray clock ticks more slowly. The behavior is so reliable that the X-ray variations have been used to measure black hole mass, including the smallest known black hole. Just 15 miles across and 3.8 times the sun's mass, it's barely above the mass limit of a neutron star. Recently, a group led by Adam Ingram at the University of Amsterdam combined X-ray data on variability and the shape of the iron line. He started working on quasi-periodic oscillations for his PhD in 2009 and says, quote, "It was immediately recognized to be something fascinating because it is coming from very close to the black hole." End quote. Using data from 2 X-ray satellites, his group showed that the orbiting material was caught in a gravitational vortex created by the black hole. Quote, "It's a bit like twisting a spoon in honey. Imagine that the honey is space, and anything embedded in the honey will be dragged around by the twisting spoon." End quote. They chose a black hole with an oscillation time of 4 seconds and observed it carefully for nearly 3 months. The iron line showed exactly the behavior expected from general relativity. Quote, "We are directly measuring the motion of matter in a strong gravitational field near to a black hole," end quote, said Ingram. It's still one of the very few tests of Einstein's theory in this regime. Quasi-periodic oscillations have also been seen in active galaxies. The timescales of variation are hours to months rather than seconds. The exciting implication is that accretion disks behave in similar ways over a huge range of physical scales, from stellar black holes to supermassive black holes in distant galaxies. That's the end of that section. That was a shorter one. Parzival said they've read Astrophysics for People in a Hurry by Neil deGrasse Tyson, and there's no pictures? There's like no figures at all? That's crazy. That's very surprising to me that it wouldn't include any sort of images for something that's so marketed to the public. That's wild. That's crazy. Yeah. All right. I mean, I guess it's for people in a hurry, but like, you don't have to really rush if you're just looking at a picture. I don't know. That's funny. You said it's a really good book, though. I have been meaning to read it. Forever ago, I got, I think it's called Welcome to the Universe. And I have read like half of it and then left it at my parents' house or something and kind of forgot about it, you know? We going outside the solar system. Yeah, that one's a good one. But I haven't read, honestly, too many. We have a few here. I need to read more. I want to read some Carl Sagan. He was a great science communicator. I really like a lot of his stuff. I've watched a lot of his stuff, and I've watched some of Neil deGrasse Tyson stuff. But I was going to show you guys the Dropbox link that Student McLeod sent. So this is that frame dragging, so you can see how like the regular space-time is being bent and like curved into the black hole, and then it just hits a singularity at some point and probably all combines and things. But it's cool. It's a cool image. Cool stuff. There we go. What book do I want? Like an astrophysics book or like an anything book, because they're very different answers. Oh, you mean any book that you can, wow. How do you do this? I actually don't want to ask how you do this. I'm a little spooked by it. I have some books of Carl Sagan's on my bookshelf over there, actually. I just haven't had the chance to read them. I feel like I have to be in a mood to read nonfiction, you know what I mean? Especially like the dense stuff. But I also have access to the LA Public Library, and they have everything. It's insane. Granted, it's like one of the biggest cities in the world, so it makes sense. But we have a lot of books. I'm actually reading a series of these graphic novels, and they're from like the early 2000s, and I got into them because I watched the show that oh no, I'm okay, Parsel. Well, thank you. I appreciate it. But they have like 30 copies of each of these editions of these books just in my library system, and I'm like, where do you keep all of those? That's so many books, and no one's checking them out except for me. They're from early 2000s. They're for like teens and young adults, and they just have so many. It's crazy. But anyway, are you guys looking at any books? I am a nerd. Yes, I've embraced that. But are you guys asking for any books for Christmas? Are you given any books for Christmas? Are you hoping to get something from a family member or something like that, or a significant other, friend? Any astrophysics books, any stuff? Are you going to use any gift cards to get things? You treating yourself? Let me know if there's any that are like on your list that you're looking to read, because honestly I feel like I've missed a lot of what's been published this year, just because this year's been ridiculous and a lot of things have been delayed and stuff. But let me know. Okay. When a black hole eats a star. What happens when a supermassive black hole eats a star? In 1998, Martin Rees ventured an answer. He had been thinking for years about how it might be possible to detect the dark black holes that should lurk at the center of every galaxy. He thought about what might befall any unfortunate star that ventures into a region of extreme gravity. As it gets close to the black hole, the star is first stretched and then ripped apart by tidal forces. Some of the debris is ejected at high speed, and the rest is swallowed by the hole, causing a bright flare that might last for several years. Stars avoid this fate unless they travel very close to a black hole. Every black hole has a tidal disruption radius. Outside this limit, stars maintain their shape. Once a star enters this space, the destruction begins. About half of the star's mass is ejected, and the other half moves onto elliptical orbits that gradually deliver the gas into an accretion disk. The black hole feeds on this material just outside the event horizon, and the conversion of gravitational energy into radiation makes a bright flare. Sometimes the event triggers relativistic jets, and we have a figure of that. Every time I switch to the PowerPoint, I get very nervous that it's going to crash, but we're going to try it. That's the wrong one. There we go. So here's a figure or a demonstration of what they're talking about. So we got the sun-like star on an eccentric orbit plunging toward this black hole. When it gets close enough, the star gets distorted by the tidal forces, and then it starts to, form into an accretion disk that is slowly going into the black hole. And then the black hole, the particle jets form as particles are being expelled. Yeah. All right. Where was I? There we are. Imagine the sun approaching the black hole at the center of our galaxy. Nothing would happen until the sun was within 100 million miles of the event horizon. Then the sun would be torn apart and all the planets, including the Earth, would be scattered like 10 pins, with an equal probability of being ejected to safety or consumed by the black hole. Approach that close is unlikely, so tidal disruption events are rare, occurring about once every 100,000 years per galaxy. For a sun-like star approaching a central black hole of a few million solar masses, the radius of tidal disruption is far outside the Schwarzschild radius. But the Schwarzschild radius grows linearly with mass, while the disruption radius grows more slowly. So black holes bigger than 100 million solar masses consume stars before they can be ripped apart. Think of big black holes swallowing the carcass whole, while smaller black holes tear the meat off to eat it. Also, the fate of a star depends on its size and stage of evolution. Large stars suffer stronger tidal forces. So a red giant heading into the galactic center would get disrupted much farther out than the sun would, while the white dwarf would disappear inside the event horizon without being disrupted. Numerical simulations suggest that the accretion rate after a disruption event is sensitive to the mass of the black hole. If the simulations can be trusted, the time between disruption and peak flare brightness might be used to weigh a black hole. For a star like the sun, that time delay is a month for a black hole 10 to the 6 times the mass of the sun. And the time delay increases to 3 years for a black hole 10 to the 9 times the mass of the sun. What do these observations say? About 20 tidal disruption events have been seen with X-ray telescopes, including a couple where the accretion is so efficient that the brightness far exceeds the limit defined by Eddington a century ago. A small set of events showed that a surge in accretion can power the relativistic jets that are seen in radio quasars. All of these examples are in distant galaxies, so astronomers got very excited when they realized that a gas cloud called G2 was heading for the black hole in the center of our galaxy. In late 2013, the gas cloud passed very close to the massive black hole, and nothing. But a year or so after that close passage, the rate of X-ray flares increased by a factor of 10 to 1 a day. This has led to speculation that G2 was not a gas cloud, but a star with a large envelope, so that it would have taken longer for material to be ripped off and descended into the black hole. The show isn't over. After 15 years of gathering data, X-ray astronomers are waiting for G2 to make another pass. The anticipation is only slightly dimmed by the fact that everything we are watching in the galactic center happened 27,000 years ago. Meanwhile, optical astronomers have their eyes glued to S2, a star that loops around the galactic center black hole every 16 years. They have a new tool called gravity, all caps, that combines light from the 4 8.2-meter telescopes of ESO's Very Large Telescope to give the angular precision of a single telescope 130 meters across. In 2018, S2 will pass very close to the black hole and provide an unprecedented chance to test general relativity. It's expected to pass just 17 light hours from the event horizon, traveling at 3% of the speed of light. It may be ripped apart or devoured entirely. The destruction of a star by a black hole certainly captures the imagination. In 2015, it led to a news story pushing a culinary analogy. Quote, "Black holes devour stars in gulps and nibbles." End quote. That spawned this overheated headline in England's Daily Mail newspaper. Quote, "Echoes of a stellar massacre. Gasps of dying stars as they are torn apart by supermassive black holes are detected." End quote. Apart from the fact that stars don't have feelings, they don't make sounds, and sounds can't travel through a vacuum, the headline is quite accurate. That's the end of that section. You said your small brother might get a Barbie. Oh, we have a black hole swallowing a star. Ooh, fun. You guys always get me such good images and things. Let's pull that up. I'm trying to close some of my tabs. Too many tabs open. There it is. There's a black hole. Just eating a star. Just murdering it. Parzival, you're asking why do babies cry when they so quick when they get taken out is because they're not ready. They're not ready for what this world is. I don't know. That's more of a biology question, I think, than a oh my gosh. Fun meme from Parzival. But yeah, that's a really nice image. I like this one. It's a funny meme too. Because we live in a simulated world controlled by aliens. Maybe. Hey, I mean, you know, it's possible. But, I mean, I feel like Chris has gotten this question asked a lot before. Like, do we live in a simulation? And it's like, maybe. But will it change anything? Not really. You know? Yeah, Student McLeod said, I think you should bring that up in the biology course you take. Yeah. There's, doesn't Chris teach an astrobiology course? I think he does. I'm pretty sure I edited that for him. I've edited a few of his courses. Too many. I can't keep track. All right. You finished his astrobiology. Yeah, I thought he had one. I know he has the history of astronomy as well. Or that was a U of A course and he's going to be putting it on soon, or he put it on already. I'm not sure. He has a lot of courses. But yeah, astrobiology is a good one. Born, live, die, why? Is that entropy or something? Entropic time? Space-time? Stuff. You said it's a theory that NDT is brought up before. Who's NDT? I don't actually know who that is. While you answer, I'm going to go on to the next section. Oh, Neil deGrasse Tyson. That makes sense. I will not go on to the next section because I got a question. How does Professor Impey have the time to do all the things he does? You know, I have been wondering that since I started working for him. I honestly have no clue. I know, right? Like this past semester, he was teaching a class at the university. He was working on grants to fund our program here, like what we do here. He's also working on other projects. He's working on an app that has to do with some science stuff. I don't know how much I'm allowed to say about that, so I'm not going to say too much. But he's working on an app with our computer programmer. He's doing that class. He's doing these Q&As. He's developing a new class. He is doing some other educational research, I believe. A lot of his research now, like he used to do a lot of research of just like on black holes and things like that he's talked about in the book. But a lot of his stuff now is more educational research and how to like do outreach and things like that, which I think is really cool. And he did also have dean duties. I think this was his first semester, or last spring was his first semester of not being assistant dean or associate dean. I don't know if he actually still has the title right now. I'm pretty sure he may have stepped down because he was doing too much, but he is I don't know how he does it. It's extremely impressive. And he's a really cool guy. He's honestly like a really good guy to work for. Yeah, he's a good boss. He's a really good boss, and he's a really good person. Is he going to be doing a more math-based astronomy class for Coursera? I'm not sure. I know he's working on one that's coming out. I think they said in like February, maybe, or March, at some point in like late winter, early spring. I think they're launching a new course, and I'm actually not sure what it's about. I didn't edit this one. I don't know who edited this one, because I don't know who else is on the team anymore. Is he working with any postdocs? I don't think so. He has, so Matthew is also a doctorate. He's got his doctorate in education. And he is kind of Chris's like, his title is like educational program manager. So Matthew kind of runs what we do here and what Active Galactic was doing and stuff like that. So he does have Matthew to help him with a lot of stuff. And then I don't believe our computer programmer might technically be postdoc, but I feel like he's not. I think he might just be just a regular employee. So technically not postdoc, but he has finished his master's degree in computer science and stuff. So I guess not postdoctorate, but some people that are not students, essentially, is what I'm saying. But yeah, we do have a small team. There's like me and Michael and a couple new student workers, Chris, Matthew, our computer programmer. That's pretty much it. He also has family in Tucson. Yes, he lives and works in Tucson. Matthew's not a student. No. Matthew got his degree from Chicago? School in Chicago, maybe? Or maybe he finished in Arizona. I'm not sure. But no, Matthew already has his PhD and everything. He's just an employee now. So, yeah. Matthew doesn't teach. He just runs these programs. So, yeah. Cool stuff. All right. I will start this next section now. Taking a black hole for a spin. Black holes are remarkably simple. The no-hair theorem says they're described by just two numbers, mass and spin. We've talked in the first part of the book about ways to measure black hole mass, which usually involve an orbit with a visible companion. If the black hole is a collapsed star, or if its effect on the motion of nearby stars, or if it's massive enough at the center of the galaxy. But what about spin? Gravity doesn't depend on rotation in Newton's theory. But in Einstein's theory, mass couples to the geometry of space-time. In 1918, it was predicted that rotation of a massive object would distort space-time, making the orbit of a smaller nearby object precess, like the pivoting of a spinning top. This twisting of the contours of space is called frame dragging. Recall Poe's vivid description of the maelstrom. As with other subtle effects of general relativity, the first place to look is close to home. The Earth twists space-time as it spins, but the effect is so minute that for decades it was considered impossible to detect. In 2004, NASA launched a satellite called Gravity Probe B to measure space-time curvature caused by the Earth, and the even more subtle frame dragging caused by its rotation. The tools for the job were 4 gyroscopes the size of ping pong balls. Gyroscopes are often used to guide spacecraft, their rotation axes pointed in a fixed direction. The gyroscopes on Gravity Probe B contained quartz spheres coated in niobium. I've never heard of that. They're among the most accurately machined objects ever made, spherical to within 40 atoms. If scaled to the size of the Earth, the highest peaks and valleys would be no larger than a person. They were shielded from their containers by a thin layer of liquid helium. At that temperature, the spheres became superconductors, and the electric and magnetic fields they generated were used to keep them aligned. Gravity Probe B began its 16-month mission 50 years after it was initially funded. Wow. The gyroscopes locked onto a bright star in the constellation of Pegasus. The satellite measured space-time curvature by the tiny angle the gyros leaned into the gravity of the Earth, and it measured frame dragging by the even tinier angle the gyros lagged the spinning Earth. Unexpected noise reduced the sensitivity of the experiment and slowed the analysis. These headaches meant that final results weren't published until 2011. Einstein's prediction of space-time curvature were confirmed to within 0.5%, and his predictions of frame dragging were confirmed to within 15%. When the dust settled, Gravity Probe B was shown to be a successful, although exhausting, technical tour de force. And we have a figure here. Nope. Here. There we go. So this is an image of gravity probe B. So it tested two particular predictions of general relativity and the weak field situation of Earth orbit. So this is just showing you kind of what it was doing. Testing Einstein's universe, it says. So it was 642 kilometers above the Earth, and it was measuring this geodetic effect and the frame dragging effect using Pegasi as a guide star. Cool. Spin has a different implication for low and high mass black holes. Black holes in binary star systems are more massive than their companions, so their spin won't change much due to that interaction. Their spin rate is a direct relic of their formation in a supernova explosion. Massive black holes, by contrast, grow over cosmic time by consuming gas and stars in their inner parts of the galaxy, but also by mergers with black holes in other galaxies. So the spin of a massive black hole encodes the history of its growth through accretion and mergers. Therein lies the motivation to make this difficult measurement. Oh, and you have another diagram of a couple diagrams. Oh, you said niobium is like a titanium? Oh, okay. I mean, I figured it was some sort of element. It's just not something I had ever really seen before, you know? Okay, let's see. Ooh. So here's... Is that a gravity probe diagram? Is it in there? Oops. I guess this is just showing that frame dragging, I believe. And then... What's this one? Oh, here we go. Yeah, so it's showing the frame dragging and the and then here's the gravity probe B and the star that it locked onto here to test those theories. Very cool. Your Pegasi? All right. Spin has been measured for several dozen supermassive black holes. Most often, the measurement uses the shape of the iron spectral line when it is reflected off the inner edge of the accretion disk. From 1 million to 1 billion solar masses, most black holes spin between 50% and 95% of the speed of light. Such rapid spin rates suggest the black holes grew after a single major merger with another galaxy, where most incoming material arrives from one direction, as opposed to being built by many minor mergers of material coming from different directions, which would average out to a slow spin rate. The best way to measure spin is by using the types of data that probe the inner accretion zone: spectroscopy of the iron line, quasi-periodic isolations, and the rare tidal disruption events. What's the limit on the spin rate of compact stars? For neutron stars, the rotation rate can only be measured for the subset in which a hot spot emits radio waves that sweep across the sky like a searchlight. The fastest pulsar spins 716 times a second. Theory suggests the limit is 1500 times a second, above which the neutron star would break apart. The maximum spin rate for a black hole isn't set by the structure of matter, since all information is hidden by the event horizon. It's set by a spin rate, where the circumference of the event horizon would be moving at the speed of light. GRS 1915 plus 105, 35,000 light-years away in the constellation Aquila, is spinning at a blinding 1,000 times per second. That's over 85% of the maximum rate. Archetypal black hole Cygnus X1 doesn't spin quite as quickly, but its rate of 790 times a second is 95% of the theoretical limit. Let's try and visualize these whirling dervishes. GRS 1915 plus 105 is 14 times the mass of the Sun. So it has a Schwarzschild radius of 42 kilometers. Imagine this black hole hovering in the upper atmosphere above London. It would be a dark blot covering a tenth of the sky, and it would cast a shadow not only on London, but over much of southern England. Even though it's 300 times smaller than the Earth, it's far more massive than the Sun. The turbine of a military jet engine is spinning so fast that it emits a note 2 octaves above middle C, in the range of a soprano singer. If this black hole could make a noise, it would be at a similar pitch, even though the black hole is the size of a large city. At the other extreme, let's think about the large member of the black hole binary in the active galaxy OJ287, which is 3.5 billion light years away. The mass of the black hole is 18 billion times the mass of the Sun. Its Schwarzschild radius is 50 billion kilometers, and it's spinning at 100,000 kilometers per second, or a third of the speed of light at its equator. This situation is harder to visualize, but let's imagine the supermassive black hole is lurking somewhere in space above the solar system. It's 10 times the size of the solar system, but has the mass of a small galaxy. A black hole this size has more leisurely spin rate, but it still manages to rotate once in 5 weeks. For comparison, to show how bizarre this behavior is, an object in the solar system following Newton's laws and located at the same distance from the Sun as the event horizon of this black hole would only orbit once every 5,000 years. Nothing in the nearby universe prepares us for such extreme motion. That's the end of that section. No, it's I am Pegasi. Yeah. Thought you were just being like, oh my gosh, I'm so Pegasi. Crazy. That's funny. All of that about a black hole over London, such a vivid writing. He might just have a future as an astronomy writer. Yeah. He has really great, he has really great analogies for things. He's also just very good at explaining stuff. That's why I've been able to learn a lot of things through him without having the extensive mathematical background. I think that's why a lot of his courses are so effective too, and so many people like his public courses, because it makes sense. He can make it make sense, and he uses really great visual aids and stuff. He's a good science communicator. It's hard to be a good science communicator. He does it very well. All right. Looks like we have just one more section left. It's a little long, so I'll probably break in the middle. And that's the end of the chapter. So, the Event Horizon Telescope. We're swinging for the fences. Shep Dolman is sipping cocoa leaf tea to combat the effects of altitude at the top of a 15,000-foot volcano in southern Mexico. Despite these optimistic words, the night isn't going smoothly as he fights problems with the instrument and his radio telescope steadily fills with fresh snow. If something is dancing around the edge of the black hole, this is in quotes. If something is dancing around the edge of the black hole, it doesn't get any more fundamental than that. Hopefully, we'll find something amazing. End quote. Dolman was a physics student at Reed College in Portland, Oregon, where science students ran their own nuclear reactor, and the air in the student union was often thick with marijuana smoke. Wanderlust led him to take 2 years off before graduate school and spend most of that time doing scientific experiments in Antarctica. As a graduate student at MIT, he tried plasma physics and geology before settling on radio astronomy when he saw the beautiful maps of quasar jets produced by the technique of very long baseline interferometry. Dolman realized this technique offered the best chance to take a picture of a black hole, and he knew exactly where to look. The ultra-compact radio source in the direction of Sagittarius, called Sagittarius A star. The center of our galaxy is a compelling target for this research. Apart from the fact that it has the most convincing evidence of any black hole candidate, it's also the easiest to study. The angle subtended by the event horizon of the black hole at the galactic center is 50 micro-arcseconds. As a tiny angle, but it's 10 times easier to resolve than the event horizon of supermassive black holes in external galaxies, and several thousand times easier to resolve than the event horizons of the nearest stellar mass black holes. So it has become the watering hole for astronomers wanting to probe a black hole and test general relativity in a new way. Dolman is the young leader of a project called the Event Horizon Telescope. Also, preface, this is all before the Event Horizon this was written before the Event Horizon Telescope got the picture, I'm pretty sure. So, the Event Horizon Telescope isn't a single facility. It's an array of 11 radio telescopes spread around the world. Dishes from Chile to Antarctica to Hawaii to Arizona to Spain all act in concert to mimic the imaging sharpness of a single telescope the size of the Earth. Operating a telescope as big as the world requires atomic clocks accurate to a second in a century. Astronomers from 20 institutions are working on the project. Data is gathered at short radio wavelengths of a millimeter or less. Millimeter radio waves are affected by water vapor in the atmosphere. So most of the telescopes are in cold, dry locations. As a result, Dolman has not only watched telescopes filled with snow, he's had to wear an oxygen mask to test equipment at an altitude of 16,000 feet in the Andes, and he suffered risks to his extremities using a telescope at the South Pole. A group of 30 scientists and engineers run the radio dish on Kitt Peak in southern Arizona that's a vital part of the array. My University of Arizona colleagues, Ferial Ozel and Dimitrios Psaltis, are using numerical relativity and ray tracing on a powerful supercomputer to calculate the appearance of the black hole. Another colleague, Dan Marone, winters over in our Antarctica every year to tend another antenna in the array, the South Pole Telescope. These scientists are in their 40s, part of a generation that's determined to get to the bottom of black holes, at least metaphorically. In the quest for higher and drier observing sites, the South Pole can't be beat. The dome of ice rises 8,500 feet above sea level, and the humidity is less than 10%. All that water is frozen into ice as hard as granite underfoot. I hope to go someday, but I think I'll forgo that endless winter night when the gales howl and the temperature hovers around negative 60 degrees Celsius. If you winter over at the South Pole, you have to be very confident of your sanity and that of your colleagues. Bring a radio astronomer. Dan Marone doesn't need a dark sky to detect... being a radio astronomer. Dan Marone doesn't need a dark sky to detect millimeter waves, so he goes during the Antarctic summer, trading the warm Tucson winter for a temperature just below freezing, which is as warm as it gets on the bottom of the world. There's something poetic about going to a place of endless night to take a picture of endless darkness. The project already has some impressive results, and the array isn't even operating at full strength yet. Material is falling into the galactic center, and that region should be very bright, given the size measured by the Event Horizon Telescope. However, it's faint, so energy must be disappearing into an event horizon, which is strong evidence for a black hole. Early data shows that the accretion disk is seen close to edge-on, which means that our perspective allows the disk rotation to be measured, thereby putting constraints on the spin of the black hole. The variability of the compact radio source is associated with changes in the accretion flow very close to the black hole. Simulations suggest the array will soon be sensitive enough to meet its design goal, to make the first image ever of a black hole. It's so funny I just started laughing there a little bit because this was written in I don't know when he actually wrote it, but it was published at least in 2019. I believe. I think at the beginning of 2019. And by the end of the year when this was published, we had the first image of a black hole, and that's pretty cool. But I have a figure for you guys. So I'll show you that real quick. So it says, on the left is a simulated image of the black hole at the center of our galaxy. The simulation uses an accretion flow method and shows light lensed around the black hole into a distinctive ring encircling the black hole shadow. The ring diameter is 5 times the Schwarzschild radius. The image is bright on the approaching side and faint on the receding side of the accretion disk. On the right is an image with the expected performance of the Event Horizon Telescope in 2018. It's cool. What did you guys say in the chat? Oh, yeah, Student McLeod said having a PhD in astronomy does not mean someone can communicate science well, and Doc can. Yeah, definitely. I mean, it's I wouldn't say it's a rarity, but it's definitely something that you really have to work at, because I mean, it's combining two things that are like neither of them are very easy, you know. And I think the thing that a lot of scientists get bogged down by is like trying to remember that like what they're trying to communicate to people, they need to put in terms that are not so simple that they're, you know, treating the readers like idiots or something, but also they need to remember what lay people know and don't know, you know. I think when you get so into a field, like whatever you're an expert in, but especially science, but whether it's, you know, science or technology or literature or whatever, you can forget like what a layperson would know and wouldn't know about your field. And that really, like, you need to keep, it all comes by experiences and like figuring out like, because he does so much work with people. I think that helps a lot too. He does so much work in like even the classes he teaches at the U of A, they're usually general education classes. They're either like very early in the astronomy track, or they're just for students like me, where I was doing film and television, but I took a astronomy class, you know. It's hard to do science communication really well. That's a very random question. Who am I a fan of in EDM music? I don't really listen to a lot of EDM, to be honest. I mean, I'll listen to some, like, what is it, Chainsmokers? Are they EDM? I'm not sure if they count. I'm listening to a lot of Miley Cyrus. I know she's not EDM, but she's great. You're not surprised he would write about Antarctica? He said the South Pole, really? That's really funny. That's such a good question. That's fun. Yeah, that sounds chilly. I want to go to Alaska. I don't know about the South Pole or the North Pole. Both sound too cold for me, but I want to go to Alaska. Because I think that'd be really cool. I wrote about Alaska. It's where my second season of my podcast took place. I have a podcast. All right. There's just one more paragraph, so I'll finish this off here. So they're talking about the black hole image. The image, if it can be obtained, will be a small, dark circle of nothing. General relativity says the shadow will be 50 million miles across, which, as seen from the Earth, is like the size of a poppy seed in New York as seen from Los Angeles. The silhouette will be doubled in size by the gravitational bending of light, and rimmed in light from surrounding stars. If the image isn't exactly circular, it will be evidence against the no-here theorem of black holes. But if the image has the shape and size predicted by relativity, it will be the best visual evidence yet that space and time really can curl into a ball, and 4 million suns can disappear with barely a trace. And that's the end of that chapter. You've been thinking about swimming in outer space. My hero? Who's my hero? Miley. That's a picture of Miley Cyrus. I just like her music a lot. I was also in the generation of watching like Hannah Montana and stuff on Disney Channel, so I was a big fan of her then. I'm a big fan of her now. My partner likes Metallica. So I've listened to some Metallica. But you were also in that Disney generation, yeah. All those live shows, Sweet Life of Zack and Cody and stuff like that. My tea is cold. But I guess it is an appropriate time for the tea to be cold, because I think we are pretty much finished for today. So thank you guys all for joining me. I really appreciate it. Like I said, I think I'm going to take next week off for the holidays, but then I will be back in the new year. Very exciting, 2021. Hopefully it's better than this year. How could it be worse? I'm going to knock on wood for that. Not even that superstitious. I'm a woman of science. but I don't trust it. I don't trust life. Hopefully it'll be better though. Oh, you said Antarctica is where they might simulate future Mars missions. That's cool. If you want to learn about where they simulated some moon landing stuff, they did that in Arizona. We made a video about it. But yeah, they did some of that in the Arizona desert. The trailer of 2021. What's the temperature now there? Here or in Antarctica? Because here it's like 63 or 64 Fahrenheit, which is... Oh, no, just kidding. It's like 72 Fahrenheit, which is... Hold on. 22 degrees Celsius. 22 degrees Celsius. Is there going to be another news discussion stream this week? There will. We're probably mainly going to focus less on news and more on the... Well, it's news, I guess. But we're going to be talking a lot about the conjunction of Jupiter and Saturn, which is happening today. So we'll be talking a lot about that. Probably just kind of hanging out because it's the day before our like Christmas break sort of thing. So yeah, come hang out. It'll be on Wednesday. I have to check the time because Michael is not in Arizona anymore, so I think his schedule may have moved a little bit. Is it cold? I don't think it's cold. I guess you're in a much warmer place. So, but yeah, we'll be talking about the conjunction of Jupiter and Saturn. Yeah, Single Coded said it's well worth to look at it. Even if you don't have a telescope, it's even cool to just see it with the naked eye because like it is definitely something you can see with the naked eye. So yeah, go check it out tonight. Take yourself some pictures. If you want to share your pictures, also whether you just take them with your selfie or your phone camera or with a DSLR or with a telescope or whatever, if you guys take any pictures, post them in the Discord for Twitch streams and we can look at them and stuff. It'll be cool. Yeah. Oh, it's too cloudy where you are. Oh, I'm so sorry. Hopefully it'll clear up for you, and if it doesn't, also I know there's a bunch of people that'll have like amazing photos of it too, so you'll be able to see it eventually. Oh yes, and I will find that movie. I'm gonna watch that 2010. I gotta watch that. Do some holiday movie watching. All right, well, I guess I will leave you guys here. Tomorrow there should be a Q&A with Professor Impey, the same time this one started, so 10 o'clock for me, different times for you guys. And yeah, Merry Christmas to you guys as well if you celebrate. Happy holidays. I know Hanukkah has already ended, but I hope you had a happy Hanukkah. I do not know when Kwanzaa is observed exactly, but if you celebrate Kwanzaa, if you celebrate any other holidays that I am forgetting, if you don't celebrate at all, but you're just, having a regular week or enjoying, this end of the year season, enjoy it. Have a happy new year and a safe celebration, whatever you guys are doing. And yeah, I mean, I'll be saying all of this again on Wednesday, but if you guys can't make it, I hope you guys have a good holiday season, and I'll see you next time. Thank you. Bye.